the CSF space, so basically coating the brain with hundreds of thousands of devices, or injecting them into the vascular system if we can get them really, really small, like sub-erythrocyte size. And the job of these things would be to go in or around the brain, measure voltages, and then put people in a conventional MR scanner and have the scanner power the devices with RF pulses, so that the power doesn't have to be on the devices. Provide enough power for the devices to sense the local voltage, and then have the device transmit not back out to the outside world, which takes a lot of power and a lot of communication, a lot of coding, but only into the local environment. So make local perturbations via pulses of RF or DC magnetic fields that are MRI visible. So then the key hypothesis is that it's useful to consider quantification and spatial localization performed by the MRI system. And so we're in the first year of the project. We're still very much in relatively early design phases. The folks at Gert Kauenbergs and Shadi Daya here at UCSD are in charge of figuring out how to make the devices. Tom Liu and I are in charge of incorporating those kinds of devices into an overall scheme that transduces the signal from electrical measurement, from reception of power from RF pulses to electrical measurement to local pulses of DC or RF fields, and then to MR visible form. So I won't go into detail about this, but on the EE side, there are groups here that, the Shadi and Gert's group have a tremendous amount of experience in very small, biocompatible nanodevices, and what we're doing on the MR side is basically, back of the envelope calculations to figure out how much power we need and what it would take to make local MR visible signals. So the track we're generally sort of focused on is having the devices actually create RF pulses, so that the devices will be the excitation sources for exciting the MR spins, and that the readout process would actually be even easier than a normal MRI pulse sequence, in that it doesn't need to do excitation at all, and all it's doing is rastering gradients through K-space and doing the readout. So that's our current approach. We think with relatively conventional design and fabrication methods, we can get certainly to the sub-millimeter scale, which is sort of what it would require to inject a bunch of these things over the cortical surface in the CSF space. Obviously, we need to do a lot of scaling farther down in order to get down to vascular sort of scales. But within this first 2-year R21 project, we're mainly focused on the key, central design considerations: how to get energy to and from the devices, how the detection self-excitation work, and generation and modulation of the local fields. There's a host of very important effects that we'll deal with in the second phase if the initial proof of concept pans out. Okay, so that's a brief overview of that project. The other project that I'd like to talk a little bit about or give an overview of is actually one that's kind of scary to present right after a whole morning of greatly detailed discussion about what underlies the Bolt signal, because this is sort of the opposite top-down approach, taking the Bolt signal and saying, well, it's just a bunch of numbers, and I don't care where they come from, and I'm going to see, so there's now these large data sets of fMRI data out there, and asking sort of from the top down what's in the signal, from like a machine learning computational point of view. So as you probably know, one of the cornerstones of analysis methods for fMRI data is correlation analysis in a bunch of different forms. For resting state data, what's commonly done is you do correlations between the signals from different regions, and you use that to do something. You do various things, but something like create edges for graph analysis. And I think most of you also are aware that a couple of the main shortcomings of correlation-based analysis is that they sort of inherently give you connections that are symmetrical, that is, non-directional in time. In fact, not only are they typically non-directional in time, they're worse than that. They're actually agnostic of time, in the sense that if you take all the numbers that you get and you scramble them in time, the correlation's unchanged. Right? So they really don't inherently incorporate continuous time features of the data. So we sort of made the very naive, or asked the very naive question, despite the fact that there's a hemodynamic response that mushes things out, can we learn anything that's directional in time from the data that's in resting state fMRI signals? We're doing this sort of big data style, using hundreds of subjects from the Human Connectome project, and building the very, very simplest possible model of that's dynamic, that has a direction in time, that's and that is one that linearly predicts time point A from time point A minus 1. Literally that simple. And asking whether the weights or that you would learn from such a model would give you information that's at least different from that you get from correlation, and hopefully with some directionality in time built into it. In the simplest form, it's the same thing as vector autoregression, so if you're more familiar with that language. What we're actually doing is taking 500 subjects or so from the HCP database. There's 5,000 data points from each subject, 5,000 time points from each subject. We're using the HCP's recent multimodal parcellation to get both cortical and subcortical parcels. So we have 379 parcels per time point. And the model is literally this. You learn a linear set of weights that optimally predicts time point t plus 1 from time point t. And then ask if there's anything interesting from these weights that you can learn. So the way these weights are organized, the brain state vector is a left cortex, right cortex, and then subcortex. This is just following the gray ordinate system that's in the Human Connectome project. And this is an actual weight matrix that you learn from going through all those 500 subjects and learning the correlations, or learning the weights that you would need. So one thing you see is that there's this obvious structure to it. The stuff that's on the diagonal is not surprising. That's effectively the autoregressive model, like non-vector, but that's asking how much a voxel signal depends on its own value in the previous time point, and obviously the largest weights are along that axis, which is not surprising. What's somewhat more interesting is that if you use a pure autoregressive model, you get numbers on that diagonal that are around 2/3. So basically, if you only have the signal from your own voxel, the best estimate in the next time point is 2/3 of what it was in the last time point. But interesting, if you allow it to be a vector autoregressive model, that is to allow linear inputs from everybody else, you find that the numbers along the diagonal actually drop by half. So that is that in the process of trying to improve the estimate of the forward estimate of the signal, the autoregressive weights actually drop by factor 2, and then the predictive value is actually supported and increased by points that are off the diagonals. So there's some features. So this is an actual weight matrix that you would learn from that kind of process. And there's some interesting features. You can see there's obviously these vertical stripes, which we'll talk about a little bit more. And the other thing you'll notice is that the weights are very, very much more sparse. Other than these vertical stripes, the weights are very, very much more sparse than you would see in a regular correlation analysis. So this is a conventional correlation analysis from the exact same data, which typically shows this blocky kind of structure, which indicates that there are these communities of voxels that talk to each other. Our approach is much more sparse, which I think you can interpret as correlation asks, what neighborhoods talk to each other, and our method asks what is the minimal set of parcels that is needed to provide an optimal prediction. And that apparently from the data is a small subset of the communities themselves, which are these blocky structures. If you do partial correlation and regress out time point n minus 1 from the data, it increases the sparsity a little bit, but not that much. So it's really quite different. and I'll speed through the rest because I think I'll try to help us stay on time. The vertical stripes indicate means that there are areas of the brain that are strong predictors of future global signals. And if you look at where those are, you can sort of map those back onto the brain, and you can find areas that are actually these yellow areas are positively predictive of global signals in the next time point. There's strong positive signals in the brainstem, and actually the very strongest signals are negative signals in the cerebellum. So those are the most strong negative predictors of future global signals. You can also look at the eigenstructure of this weight matrix to ask, what are stable modes of this model, and they show things like in the first few components show things like the default mode network here, and visual networks and global signals and stuff that are not too surprising. Because it's an actual dynamical model, you can actually run it forward in time and predict some dynamics from it. And lastly, we're currently interested in asking whether this kind of model will help identify states of the brain. I mean, so switching between states is sort of something that many people in the fMRI business are trying to figure out how to do, figure out what a state is, what switching between those states might mean. And this is just an example where we start with actually not one model. So a model is that set of 100 and some or 300 by 300 weights, which is about 100,000 dimensional point. And what we do is start with a large cloud of potential points in 100,000 dimensional space as potential models, and allow the data to train those models that are the best fitting to those data points. And what we find is that when you start training that way, the models will actually cluster into handfuls of models that seem to be distinct. So this is a TSNE depiction of reduction of that 100,000 dimensional model space, and it shows these blobs which are suggestive. TSNE is sort of always suspicious because it can find structure in just about anything. So as a sanity check, if you take these 5 blobs that TSNE finds and run a conventional k-means, the k-means will say, okay, yeah, those are in fact different blobs. And each of these blobs will then have a different eigenstructure, and we're trying to figure out now what to make of that. But it does seem to be an approach, at least, that seems to in a relatively unbiased way, identify states of the brain. And interesting questions, for example, are like, whether the state actually means whether it defines a static state or whether it defines actually a dynamic state, because a model can describe either. An eigenstate of the model is a static state, but a dynamic state can be described by each of these models as well. So in summary, the information certainly appears to be different and complementary to correlation methods. The eigenstructure, reveals things you would expect, like default mode and global signals. Global signal actually is shown to oscillate by the eigenvalues. It can be used to construct directed graphs, which you cannot do with regular correlation analysis. It shows some interesting hints in being able to help understand the global signal. It may be an interesting way to discover characterize brain states. Numerically, it describes about half of the variance in all of the data, which is somewhat surprising to me, at least, that one matrix for all subjects for all time points actually explains about half of the variance in the data. And certainly some holes in the current model are many of them, as you saw from the analysis of the bull signal this morning. But most obviously, the hemodynamic delays are not considered at all in the model, and information on them is actually not present in the data. And this is resting state data, so for task-based data, there's some, I think, interesting ways to wire in external inputs as additional elements to the model. But I'll stop there. Thanks.